Okay, welcome everybody. This is this is the week 5 webinar. So we're moving through the class, and hopefully you're making it through. And let me tell you the plan for today. What's going to happen? I'll start out with Q&A as always, and then I will get into sampling distributions. So hopefully you realize that a big part of statistics is conducting a study, collecting data, and looking at a sample. And one of the things you want to look at is what is the distribution that you would get from a sample? So that is the plan to talk about that. And it turns out it's very special, which we'll see in a little bit. We'll also talk about unbiased and biased estimators. Then we'll get into the central limit theorem. The central limit theorem, by far, is the most important theorem in all of statistics. So it's so important, I'm breaking it into three. And the first will be the central limit theorem for means. That's when you have a question and it's a quantitative question, and you have your sample and you want to see what the distribution of the sample is, and it's going to talk all about it. Then we'll get into the central limit theorem for proportions. That's when your survey question is like a yes/no question. And you want to see the proportion of people who said yes. And look at the sampling distribution for that. And then finally, we'll look at the central limit theorem for sums. So sometimes you're not as interested in each individual data value as the total sum. If you add up all the values, what do you get? And we're going to look at the sampling distribution for sums. And there'll be a big theorem called the central limit theorem. And it's going to come up and handle all those. So I want to remind you, I want to mention a few things first, and this is really important. I pay attention to the webinars, okay? Whether you're watching it live or whether you're watching it recorded, if I say you have to use something for an explanation of something, I'm not joking. Okay, I usually highlight it, I yell it out. It's obvious if you pay attention to the webinars. Um, More than half of you didn't. And that hurts you on points on the exam on the written question because you didn't use the wording I said you have to use. And that's going to happen, multiple times in this class. So make sure that you pay attention, you write down, make sure you keep notes, whether you're watching it live or recorded, have paper and pencil, and write down what it is that you have to have in terms of wording, because I'm going to tell you that has to happen. AI is not going to give you that wording, by the way, just to note that. Okay. And it's important wording. Okay. It really gets into what's going on. So when I was grading the exam, the written question, a lot of you did not use the wording. And when I graded the discussion post assignment, a lot of you did not use the wording. And you don't use the wording, you lose a lot of points. Okay. A big percent is lost if you don't use the wording for the hand grade, the stuff I grade. So that's just a big note. I want to give you a heads up. The second thing that's really important is what's the big thing that's due on Sunday? What is it? Yeah, project one. So at this point, you should have made amazing progress, like written just about all of your draft already. Because like tonight or tomorrow, the hope is you send me your draft so I could look at it and I can give you suggestions on how to fix mistakes, how to make it better, how to add stuff that you need to put in. And, I can't help you if I don't see what you're doing. So you send the draft to me, then I'll do that. And I do read it on a first come, first read basis. And these are two sections and they're big classes. So if you all wait until Thursday, at 7 in the morning, it's going to take a long time because that's the kind of thing that takes me to, it's like 10 pages or so. And, if there's 20 projects or something, that's a lot of reading for me. And if you're the last one to send it to me, then it won't work. Okay, I won't have time. So make sure you get that in pretty soon. And after 8 a.m. on Thursday, I'll just send you an email back saying, no, too late. Go talk to a tutor or something because I don't look at drafts. And you draft by emailing me, by the way. Okay. Your final submission is going to be put into Canvas in the assignment. But the draft, you just send me an email. Okay. And then any questions you have, you post on the Project One discussion board. So that's kind of the way to do that. So there's no exam this week, but there is a project, and the project is a lot of work. The hope is that you put a lot of work into it already, so you don't have as much to do. Okay, if you haven't, then you're gonna have a lot to do. If there's only two of you in a group, please post on the discussion board saying I can accept one more person, because I have gotten one person that wants it, doesn't have partners and needs them. So that's important. Or if you don't have partners, please post on the discussion board, the project discussion board saying, hey, I need a partner. And then you can pair up with the person that needs it, the other person. Because again, you can't pass pretty much. It's pretty much almost impossible to pass if you don't have partners. Okay. So are there any questions about anything? Okay. If there's no questions, I will always let you know I'm online for my student hours. Also happy to answer questions throughout, and also at the end when we turn it off, I'll answer again. And one of the great things about today and the rest of the course is it's really easy to find applicable things. This is really important stuff. This isn't just when I'm ever going to use it. No one ever asks that because it's obvious. So we'll be talking about all kinds of good ideas. Okay. So the first thing is I have a question for you. And you may or may not know, if you know anything about baseball, then you do know this is playoff time. So what I want you to do is go online, okay? Get a second tab or something. Look up three baseball players and find the mean and the standard deviation for their ages. So I'll give you, it shouldn't take more than a few minutes. You could just go on Google. If you have your favorite team, you can pick some players from the team and type in, how old is this person on baseball? And Google will tell you, or whatever you use. Or you can just say it. That'll happen too. And let's see if you can find the mean and the standard deviation. Remember, the easiest way to find the mean and the standard deviation is you go to one variable stats in the calculator and you put in your data, your three numbers, and this is a sample, and you hit calculate. Okay, it's very simple. And I just want to let you know you are required to use this calculator for your exams and for the discussion post assignments. Okay, if you don't, I can tell. Okay, you're not getting the right answer, you're not getting the right decimals and all that. So it is important that you have to use this course calculator, which is this guy. So last week was all about the normal probability, and you're supposed to use that calculator. And I could really tell when you don't get the right answer. You're off by a little bit. Don't do it by hand. If you use AI, it's gonna be off by a little bit. Just let you know that, and then I can tell. So once you've found three baseball players and their ages, give me the mean and give me the standard deviation, which is with the calculator easy to find once you find the baseball players. Shouldn't take long, more than a minute or so. The good thing about the internet, easy to find things, especially with AI nowadays. Now you just type in what you want, it just gives you the answer for things like age of a certain baseball player. And if you don't know anything about baseball, just type in, give me a team, give me three players on a certain team, in Los Angeles, if that's where you like, or whatever. It says you need five numbers? I don't think so. Let me look. Here's one variable statistics calculator. If I put in 3, 4, 7, Sample standard deviation, hit calc. Oh, it wants five. Oh, all right. Give me five baseball players. I apologize for that. I gotta go find out. I've never seen this be a problem before. Something must have happened. So give me five baseball players and give me the mean and standard deviation. Oh, maybe it gave it. Just a minute. Yeah, it'll still give it. Yeah, you can do three. You can do three. It says it needs five, but it still does it. Yeah, I didn't make that thing happen. I wonder why. I didn't pop that in. I'll have to look at the code and see what's going on, but I did not code that. I coded this program, but I did not say it needs at least five. I'll have to look. Oh, I bet it has to do with this part, which you don't have to worry about. Yeah, so ignore that part. And it's the graphing these things, and that was written by AI. That's why. I let AI do the coding for that part. So I have to see what AI did and change it. All right, so now let's go ahead and pop in the mean and standard deviation. So mean is I'm going to go 38. I'll just do 38. Good enough. Standard deviation 9.07. All right, give me more. I need some of you to do it. Doesn't help if I just have one. So hopefully you're all doing it. Find three baseball players, give me the mean and standard deviation. Okay, 32 and 1.15. Let's see, I need some more. There's pretty many of you here, so hopefully you can do it. Let's see some more. All right, 31 and 4.92. And then we have, let's see, mean, I need a standard deviation too, not just the mean. So 27, 28, I guess I'll call it. There we go. And 3.79. All right, that's good enough. I don't want to spend the whole time just doing this. So I want to mention that we have these numbers 38, 32, 31, 28, and they're all different. Okay. And if I do lots of decimal places, you're almost always going to get all of them different. And they're all sample means. Any questions on that? So what we can do is we can look at these numbers. I'll just write them as a list. 38, comma, 32, comma, 31, comma, 28, comma. I'm just going to write dot, 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 because again, there's a lot of you. You can keep going and going and going and going. There are a lot of combinations of three baseball players, by the way. Thousands and thousands and thousands of three baseball player combinations. Okay, probably maybe millions actually. So what we have here is we have different data. We have this data, 38, 32, 31, 28. And we want to look at all the samples that could be taken. And we want to look at the distribution of all the possible samples. Any questions on that? Yeah, we're looking at three, I wouldn't use the word random, but three baseball players, ages to find the mean and standard deviation exactly. Okay? So here's the deal. First thing, I went online, and the mean of all baseball players is 29 years old. The standard deviation is 2.3. Okay? Okay, that is the mean and the standard deviation of all baseball players, which is different than the mean and the standard deviation necessarily, or it may be different, of all possible groups of three. Do you see? They're averages. So we're going to say the distribution of all sample means. Okay, we saw four different sample means, but you can get like millions of them. All sample means with the same sample size is called the sampling distribution of the sample means. So it's a little confusing because that word sample is all over the place. But this is what it is. Because when you gave me a bunch of means, that is a collection of data of means. And then we can look at the distribution of that data. And that's called the sampling distribution. Any questions at all on this big definition? Because pretty much today is going to be all about the sampling distribution and what we can get out of it. All right. So one of the things you can say, we only got, four different answers here, but there are millions of them. Imagine getting them all. And we could say, well, what is the mean of all the possible sample means of size 3? And the first thing you want to do is say, remember, the population mean of all the sample means. Population mean, we use the letter mu, that Greek letter mu, like a cat, mew, mew. And sample mean, we tend to use X bar. So the letter we're going to use is the population mean of all possible sample means is going to be mu sub X bar. And that is going to be the notation that is used for that particular big piece. Okay. Any questions on that? Okay. Just let you know, this is pretty hard to type, not impossible. I know how to do it, but I don't expect you to necessarily learn about all the typing and, in a computer. But I do want you to at least know how to say what it is. So if you want, if you don't want to write in symbols because you can't figure it out, you can write mu and you can do the little underscore thing and then X and then bar. And that's allowed. Okay. Any questions on the other way of doing it that's easy to type? For your project, if you're if you're gonna do that kind of thing, which you're not gonna be for project 1, but project 2, you should do it in symbols because that you can get help for and you have lots of time and all that. But for everything else, it's fine if you write this, but you somehow have to um, communicate. You have to communicate what you're talking about. Any questions on this? Yeah. So I see typed as mu and then the subscript and then X and then capital bar. Yeah. Because then it says what it is. If you don't want to, if you can't figure out how to do it in Greek. Okay, there's also a standard deviation. Okay, the standard deviation of all sample means. So again, we have these numbers 38, 32, 31, 28, and we can keep going, for millions of times. You can look at all those numbers, find their standard deviation. That'll be a population standard deviation of sample means. So the notation we're going to use that is sigma sub X bar. Because sigma is the population standard deviation, X bar is sample means. So maybe I'll write that down. Sigma underscore X bar. Okay, so if you don't want to have to figure out the symbols, I'll allow you to do that on, any of the regular assignments that you have to do. Okay, other than project 2, but that's another day. Any questions on that? Yeah, so for exams, if you're going to communicate, you could do that unless you can figure out the way of typing, which I don't, like I said, I don't want to require hard, kind of really difficult to learn typing. It's kind of a pain, especially when we get to proportions, you'll see. And then it gets really messy on the typing. Okay, so if we consider the collection of all possible sample means, then this is its own data set with a very large sample size. Okay. Again, there would be millions and millions of possible groups of three. Okay. All right. We can look at the distribution. We have mu sub x bar. We have sigma sub x bar. Just let you know that the word that everyone uses for sigma sub x bar, which is that population mean of all possible, population standard deviation of all possible sample means, the word everyone uses is standard error. So the standard error is a standard deviation of all possible sample means. Any questions on that? A lot of vocabulary today. Just warn you. Okay. All right. And the sampling distribution, as I mentioned, is for a statistic, it's the samples of size n is the distribution of all possible sample statistics of sample size n. Okay, so again, what we just did is when we have means, but you could also have proportions. You could also have sums. Okay, those are the main one we'll do in our class. All right, so here's a definition. A statistic is an unbiased estimator for a parameter if the mean of the sampling distribution for that statistic is equal to that parameter. So let me give you an example of one. If I look at the sample mean for baseball players' ages with sample size 3, it turns out that the mean of all possible sample means is actually equal to the population mean. Okay? That means that the sample mean is an unbiased estimator. Okay, let me give you an example of a biased estimator. Okay, a biased estimator would be if you looked at the range. If you looked at the range of the ages of the 3 players that you looked at, and you took the average of all the different ranges you could get, is that average of all the different ranges going to be the range of all players combined? What do you think? Any guess? So if you randomly just pick 3 players, do you think the range of those 3 players' ages on average will be the same as the range of all players combined? Any guess? Any thoughts? Yeah, definitely not. The range of all players combined, there's probably a 19-year-old baseball player. I have no idea, but there might be a 19-year-old baseball player is like the youngest. There might be like a, 48-year-old baseball player is the oldest, maybe 49 to make it easy. So that would be a 30-year range. Okay. My guess is none of you got anywhere close to a 30-year range of baseball players. Am I right? Because it's very unlikely to get a 30-year range of baseball players if you just pick 3 players at random. You're going to get smaller ranges, like 10 or 11 years or 15 years. Sometimes, once in a while, you might get 30, but very rare. So the range is a terrible estimator. It's a very biased estimator. Does that make sense? You would not use it to make a good guess of the range of the entire population. You wouldn't use the range of 3 randomly selected players. Okay, you ready for the big theorem? This is the biggest theorem of the whole course. And this is the central limit theorem. And I'm going to first talk about the central limit theorem for means. And here it is. Okay. The sampling distribution for sample means from samples of size n has mu sub x bar equals mu. So the mean of all possible sample means is the mean of the population, which is saying it's an unbiased estimator. Okay. Now comes the harder part. And that is the standard deviation of all possible sample means, that's sigma sub x bar, is not equal to sigma. It's not equal to the population standard deviation. It's equal to the population standard deviation divided by the square root of the sample size. Okay? If your sample size is 3, then you're dividing it by root 3, which is some messy number. If your sample size was 4 instead, then you're dividing it by root 4, which would be divided by 2. Do you see that? So what happens is the standard deviation of all possible sample means is going to be smaller than the standard deviation of the population. And if you're looking at a sample mean as a good guess for the true population mean, you want a very small standard error because then you say my guess is really close to the real answer. Do you see? Whereas if your standard error is big, you're going to say, yeah, it's kind of far. So the way you make the standard error small is you let n be very large because sigma over, say, if n was 100, then it would be 1/10 the size because the square root of 100 is 10, and it'd be sigma over 10. Have I lost anyone on this? Any questions? Okay, then part two, which is really important. One problem is if you know the mean and you know the standard deviation, that's not enough because you're not going to calculate probabilities and quartiles and all that if you don't know what the distribution shape is. But here's the wonderful, wonderful piece of the central limit theorem. If the population distribution is normal, and the or is the biggie, if the sample size is large in our class, this is important, okay? Write this down because we're going to be using this for pretty much everything we do for the rest of this entire course. A large enough sample size, when you're talking about quantitative data, means over 30. What's the very smallest you could get to be large enough? Put it in the chat box. What's the smallest sample size you can get to still be large enough to just say that the sampling distribution is approximately normal? Pop in the chat box. Shouldn't take long. What number? What would your sample size need to be? What's the smallest sample size to make it guaranteed to be approximately normal, even if you know nothing about it? This should be obvious. No, 29 is not greater than 30. Has to be greater than 30. Right? Yeah, 31. 31 is the smallest sample size that you have to really have data that you can analyze well. Do you remember what the requirement of Project 1 was in terms of your sample size? Must be over 30, okay? That was because in statistics, if you don't have over 30, it's pretty meaningless, okay? There's details and stuff I'm not going to get into because this is elementary statistics, but for us, we're calling it over 30. Sound good? Okay, 30 is not over 30, by the way. Don't have a sample size of 30. You could have a sample size of 31 is fine. Okay, now comes some interesting stuff, and this could make a big difference in your life, in your lives. Okay, this has made a huge difference in my life in terms of finances, in terms of money. Okay, and that is how do you invest money well? Does that make sense? I'm not sure how much you've learned about this, but this is a big deal. So I'm going to give you a scenario. Let's suppose that you put $10,000. Let's suppose you have $10,000. You may not, but pretend you have $10,000. And you have to decide, what you want to do with your $10,000. You don't need to spend it today. You want to invest it. Okay. This is $10,000 that you don't need today. Okay. This is for your future. One choice is you can put it in the bank. Okay. That's easy. Just go to the bank and, or use your app and take a picture of the check of $10,000 and pop it in the bank, and there you go. Okay. So the question is, what's the probability you're going to end up losing money after 1 year if you put it in the bank? And losing money means that your amount of money you win is less than zero. That's what losing money means, right? So I'm going to let X be the amount of money you gain. So the probability that X is less than zero actually is zero. Does that make sense? You put money in the bank, you won't lose it. $10,000 is called FDIC insured. And that means that even if the bank goes bankrupt, the government will still give you the money back. I don't know if you know that, but that's what FDIC insured is. Okay, I went on Google. I actually asked Google Gemini AI. I said, hey, what is the average interest rate for banks for a savings account? And it gave me 0.4%. Is that pretty good? You going to make a lot of money? No, you're not going to make a lot of money, but you're not going to lose money. Okay, so this is if you're going to die if you're going to die or you're going to have this entire horrible disaster, if it goes below 10,000, then the bank might be the way to go. Does that make sense? But that's only if there's an absolute disaster if you're going to lose money. Okay, we're talking long term. So what else might you do besides put it in the bank with your $10,000? Any thoughts? What else could you do with the $10,000? High yield savings, that's a savings account, by the way. Yeah, we talked about the average was 0.4%. Not great. What else could you do with your $10,000? That's what I would do. You could do CD, and that'll raise it a little bit, but not much. What else could you do? I don't see y'all jumping in. All right, let me tell you. In what? Cash doesn't do anything for you, then you have 0% interest. You can invest in what? All right, let me tell you. Okay, so suppose instead you put your $10,000 in a randomly invested stock. So yeah, stocks. Okay, good. Now you're saying it. All right. Now this is true. The mean for stock market investments for 1 year, by the way, is 9%. Okay. The standard deviation is 20%. Okay. So 9 and 20. Any questions on that? Okay. So your average return is much higher, but your standard deviation is way high. Okay. We're going to assume that stock returns are normally distributed. Okay. It's not quite perfect, but it's not too terrible. Okay. What is the probability that you'll end up losing money? Okay. So now with this question, what we're going to have to do is the first thing is I'm going to write X tilde N 9 comma 20. Remember what the N stands for? Very important. What does N stand for? In this N right here. I don't see y'all jumping in. It's not a trick question. You're all supposed to know. Value, no, that would be V. Yeah, N is normal, not net. It's normal. It means you have a normal distribution because it says. So that means we need to go to the calculator. So let me go back to my calculator. I'm going to go back to the calculator and I have a normal probability. The mean was 9. The standard deviation was 20. Any questions on that? And we want the probability that we'll lose money, which means less than 0. Any questions on that? And there it is. And that is, I'm going to round to 2 decimal places, about a 33% chance. So the probability that the mean, so X bar, sorry, that X is less than 0 is equal to, again, it was about 0.33, rounded to two decimal places. All right, well, that could be a problem. If there's a 30% chance of losing money, you might be a little concerned. Okay, maybe you're okay with it. Maybe if you lost, a couple $100, that's okay. But if it's not okay, then this isn't a good way to go. Is that clear? So, what's another thing you can do that's similar, but maybe more, less of a risk of losing money? Any thoughts? Okay, and I like this particular example today. Anyone watch the news about the market today? Okay, you may not know, but it was a very good day. It was a really good day. Okay. Do you know why I'm super smiling? Not bonds. Bonds don't get affected by a good day, actually. But I'm not going to get it. It's too complicated for me to get into that. I'm super smiling because I have stock and I made thousands of dollars today. Just to let you know that. It was a good day. But I lost thousands of dollars just before Friday. So you know how it is. It goes up and down. So here's another choice. Instead of investing in a single stock, let's suppose you put your 10,000 into the Dow Jones Index Fund. Okay? And you may not know, but the Dow Jones is a collection of 30 stocks. Okay? What's the probability of losing money? And we're going to assume, okay, that the Dow Jones is a representative sample and the stocks are independent of each other. So that this is really like a random sample. Okay? Then we still have mu equals 9 and sigma equals 20 and n equals 30. But now we can use the central limit theorem. And that is x bar is normal. And if you remember, mu sub x bar is just mu. There's our mu, which is 9. Sigma sub x bar is sigma, which is 20, over the square root of n, and n is 30. So now, instead of 9 comma 20, we have 9 comma 20 over root 30. Now I put that in my calculator and I got 9 comma 3.61483717. Anyone lost on what just happened? This is because we're not just doing one stock, we're averaging the 30 stocks that got bought. Do you see that? So now we can go and change this a little bit back to the probability calculator. What's new now is a standard deviation. Is that 3.6514833717? Now, let's find the probability of losing money. Any questions on that? And if I calculate it, look at that. About 0.007. Huge difference. So to let you know, by the way, in my investments, I actually don't use a Dow Funds Index Fund. I actually do my own investments, but I do diversify. And diversify means that it makes it a lot more independent of each other, so that the central limit theorem really does work pretty well. Okay. So by the way, is this risky or not risky now? What do you think? Yeah, not at all. Okay. Especially in the long term, if we're talking about like 15 years of investment, you're not going to lose money. Okay. You're gonna make money and you're gonna make 9% instead of less than 1%. So if you want to invest, let's say you're 21 years old, and let's suppose that you want to invest, you just graduated from college and now you're making decent money, you have some extra, and you want to invest for retirement, do not, you would not want to put it in the bank. Okay? What you would want to do is you would want to invest in the stock market. You'd want to diversify if you could. One way of doing that is to do an index fund. That helps you diversify, and that works. Okay? And trust me, I have been doing this for most of my life. Okay? Most of my adult life, let's say that. Okay? I also note that the standard deviation being 3.65, you're not going to lose money, but you're also not going to make, more than 20%. That isn't going to happen. Do you see? Because that'd be way above this 9%. Whereas if you invest in a single stock, you can make a whole lot of money. Do you see that? You could also lose money, but you can make a whole lot of money. So it's riskier, but it's also, you can make super money. Okay. And I do actually do that sometimes also. And I research and I look at mathematics. It can get real complicated and I invest. And I've made a lot of money that way. Not billions, I'm not a billionaire, but I have made, decent money in the stock market. Any questions on using statistics to make money? Okay. All right. So now let's suppose that you want your standard error to be equal to 2. So you want your standard error to be equal to 2. You don't want 3.65. That was, all right, but you want it, let's say you want it to be exactly 2. Then how big a sample size would you need? So now there's going to be a little math to do. So here's the math. The central limit theorem says the standard error is sigma over root n. Sigma was 20. You go over root n, and we want that standard error to be 2. Now I'm going to write it as 2 divided by 1, which is also 2. It makes fraction algebra a little easier to think about because then I can cross multiply it. I can go 20 times 1 is 20, and that's equal to 2 times root n, and that's 2 times root n. So 20 is 2 times root n. Now divide by 2 on both sides, and you get 10 is equal to root n. If 10 is the square root of a number, then that number must have been 100. So if I wanted the standard error to be 2, okay, which by the way is less than the 3.65, then instead of 30 stocks, I would need to invest in 100 different stocks. Okay, this is assuming independence. Okay, very diversified. Just let you know to make it diversified, and I do this also. Some of your money might be in international funding. Okay, not just America. So, but I do have a lot of American funds. Okay, any questions on this example here? Okay, it makes a big difference. This makes a big difference. If you just put your money in the bank, it's, the bank is going to make money. They need to make money, right? Otherwise, they're a company. They're a for-profit company. They're taking money from you, and that's how they're taking money, is they take your money and then they invest in high return investments that maybe have a higher standard deviation, but as long as it's diversified, they're fine. Any questions? And that's why the bank can do that. Okay, so now comes the next central limit theorem. We just did the central limit theorem for means, and that was when you have a quantitative question. Do you remember what the next most important thing is? Or another really important kind of question besides quantitative? That we've dealt with a lot already, or we've talked about? I don't see jumping in. All right, let me remind you. The yes-no question. The yes-no question is not quantitative, right? If I asked you something like, do you live in Tahoe? You're not going to be 70. You're not going to say 72. No, you're going to say yes, or you're going to say no. Does that make sense? So if you have a yes-no question, or a question that's like a yes/no question, then we call it a proportion. And here is the central limit theorem for proportions. Okay, so first thing is, remember we used the letter P for the population proportion? Okay, and I don't know if you remember, but we used P hat for the sample proportion. We talked about this a while back. Okay, so that's just the way it is. And it's fine. The hat on top of the P is not that easy to do in the computer. So PHAT is fine. Okay. And Q is often used as 1 minus P. So if 70% of the people say yes, what percent say no? This should be really easy. If 70% say yes, what percent say no? How many? I don't see I'll pop it in the chat box. This should be easy. If 70% say yes, how many percent say no? If it's a yes, no question. Yeah, 30%. Okay. 1 minus 0.7 is 0.3. So we're gonna use the letter Q for that one, for the percent that say no, which is 1 minus P. Okay, so then the sampling distribution for sample proportions from samples of size n has the following. Mu sub p hat. So remember that if you take a sample of people with a yes/no question, you're going to get a proportion, like say 0.38. And then you ask a different group of people with the same sample size, and then you might get 0.42. Notice you're getting the numbers. If you take the average of all the possibilities, that's a mean. So it's mu sub p hat. Any questions on that? And the big theorem is, central limit theorem says mu sub p hat is the population proportion. And here comes the one that's harder. Okay. And that is sigma sub p hat. That's the population standard deviation of all possible proportions from samples of size n is equal to the square root of PQ divided by n. Remember, P is a proportion of yeses from the population, Q is a proportion of no's, and n is a sample size, by the way. Notice that root n is in the denominator. So same as we had before, with the central limit theorem for means, we had a root n for the denominator. It's just the numerator is different. So if you have a bigger sample size, if you have a sample size of 100 more, you're reducing the standard error by a factor of 10 because root 100 is 10. Any questions on that? All right, here comes a biggie that lots of people make mistakes on. And that is if NP, which is the predictive number of yes answers, and NQ, that's the predictive number of no answers, are both larger than 5, not N bigger than 5, but NP and NQ bigger than 5, then the sampling distribution is approximately normal. Okay? So if I ask you, was the sample size large enough? And it was a yes/no survey question, do not even think about saying yes because the sample size was bigger than 30 if it's a yes/no survey question. So here's something I want you to write in the chat box. I want all of you to do this. I want you to type in, and I'll type it in first if you want also. I promise to not use over 30 when the survey is a yes/no question. You must type that in. Type that in. I want you to promise this. Do not use over 30 when it's yes/no. Okay, because you are going to use NP and NQ are bigger than 5. Okay, The reason why I'm having you type it in is this is one of the biggest mistakes students make. So now you promise, and hopefully you're one of those good kind of people that don't go back on your promises. Okay, that's why I'm having you do it, because I don't want to have to take off points. Got it? It's a big error people make. So always imagine what the survey question is, or what the data you're going to be writing down, the data, not the average result, or not the proportion of yeses, but the data. And those are yeses and nos, because that's the answer to the survey question type thing. And you don't use over 30. Okay? All right. So here is a survey question. Are the majority of Americans satisfied that Trump did not win the Nobel Peace Prize? I always try and bring real life stuff, current current stuff. Okay. And I'm not sure if you know about this, but the Nobel Peace Prize just happened. Okay. I forget the person's name, but it was given by a lady from Venezuela. Um, and it was not given to Trump. He was nominated, but he didn't get it. Okay, whether you like it or not. But first thing, I'm going to ask you a survey question. Okay, are you satisfied that Trump did not win the Nobel Peace Prize? Yes or no? Okay, notice none of you are putting numbers down. Okay, this is not quantitative, so don't even think about over 30. Got it? Ah, there we go. Yeah, someone remembers the name Maria Corina Machado. Yeah, sorry, I'm not good at remembering everyone's names, and this is when it's not like I know the person well. But she sounded like a good person. Okay. Um, so there was a sample, and they surveyed 2,725 adults, by the way. And that was the people who surveyed, that was YouGov. That's a organization that does surveys and stuff. And they found 58% of respondents agreed that Trump did not deserve the Nobel Peace Prize. And by the way, online and telephone interviews were used using landline and cell phones. They were conducted with 2,725 ballots. Okay, that's how they did the survey. So now I have a question. The question you might say is, hey, we only know about these 2,725 people. Does that tell us for sure that the majority of all adult Americans are satisfied that Trump did not win the Nobel Prize, Nobel Peace Prize? Okay, we're not for sure. Okay, good. You say no. But here's the question. If it had been 50% of all Americans are satisfied, that's like the minimum, sorry, it's the maximum amount to not be the majority. So if there were 50% of all Americans agreed that Trump did not deserve the Nobel Peace Prize, then what's the probability that of a randomly selected 2,725 Americans, at least 58% of them agree that Trump did not deserve the Nobel Peace Prize? Any questions on the question? Any questions? All right, so what we're going to do is we're going to consider the sampling distribution. The first thing is NP is 2,725, that's N. P is going to be what we're assuming, 50% of all Americans. So times 0.5. And by the way, half of 2,725 is a lot bigger than 5. And if you take NQ, that's 2,725 times 1 minus 0.5. That's also a lot bigger than 5. It turns out to be the same number, but it won't always be for other examples. But they're bigger than 5. So because they're both bigger than 5, the central limit theorem says the sampling distribution is approximately normal. Any questions on that? All right, so now we can say that p hat, that is the sample proportion, the distribution of sample proportions is approximately normal. Notice that we assume that p is 50% or 0.5. And then we pop it into this big formula, square root of PQ over N, which is the square root of P is 0.5. 1 minus 0.5 turns out to also be 0.5. Okay? Divided by N, which is 2,725. I did that division, I got around 0.01 for the standard error. So we have normal distribution, zero point 0.5 and 0.01. Let's find the probability now. So now our mean is 0.5. Our standard deviation was 0.01. The probability is what we want to find out. Okay? We want to see what's the probability that we're going to be greater than 0.58. Because that's what we got with our sample. And hit calculate. So let me ask you, and this is really important, is the probability about 6.66? To 2 decimal places? Is that the probability? Point. Yeah, so here's the thing, and a lot of people make this mistake. You always have to look to the very far right. And by the way, if you're using a smartphone, sometimes your screen's too small. It won't even show that. And you gotta roll it over. You got E negative 16. That means we need to move the decimal place 16 places, which means you're going to have 15 zeros before that 666. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then 666. So that was the probability. Okay, so if this is what they got, what are you going to say? They got super, 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 super lucky, or do you think something else might be wrong? What do you think? And this is a big part of what this course is all about, by the way. We're going to be doing this over and over again for the rest of the course. Yeah, we're going to say something's wrong, and here's what we're going to say is probably wrong right here. We assumed that 50% of all Americans agreed that Trump did not deserve the Nobel Prize. Okay? That's the big assumption we used. That's that can't be right. Okay? I mean, we're not going to get that lucky, right? That's such a small percent chance. It's like, no. So we're going to say this has got to be wrong. And it's the majority. And then you can actually put in your article, which is what they did, that the majority think that Trump did not deserve the Nobel Peace Prize. Any questions on that? Okay, so that's a big deal. Okay, so there is I'm going to write tiny, and tiny just means this like really small number. I don't have to type it again. There is a tiny probability that if 50% of all Americans agree that Trump did not deserve the Nobel Peace Prize, and if they surveyed a new group of 2,725 randomly selected Americans, then there would be and this chance is almost 0% chance that at least 58% of them would agree that Trump did not deserve the Nobel Peace Prize. Any questions on that? Any questions? Okay, this is really the most important idea we're going to have in the entire course. And this idea is going to be used over and over and over again every week for everything we do, except next week, it turns out. Next week, we're going to do something called confidence intervals. And then after that, we're going to spend our rest of the entire course doing this. But we're going to do this in lots of different situations. Any questions on this example? Okay. Now, the last one to talk about, and this is really important, is the central limit theorem for sums. Okay. So let me tell, when do you think you'd be more interested in finding the sum of something than the average of something, of a sample? When do you think you'd be more interested in the average than the sum of a sample than the average of a sample? What situation? Any ideas? There's one really big one. There's a lot of others, but there's one that comes up all the time. Okay, you may not know, so we'll get to it. Okay, but we do want to look at some. So first thing is that if I told you if I sampled 100 people and the average was 2.5, what would the sum be? So if I surveyed 100 people and the average was 2.5, what would the sum be? Well, what is a sum? It's pretty simple. I don't see y'all jumping in. This is easy. Okay. If the average was 2.5 and you surveyed 100 people, what is the sum? It wouldn't be 50. It wouldn't be 500. No, maybe I should do it. So if the average of 100 people was 2.5, then the sum was 250. How did I get that? How did I get 250? It's very simple. Very simple math. Um, I didn't divide. Remember, I didn't tell you this part. I didn't take 100 divided by 2.5. That'd be really hard, or it'd be harder. Yeah, I multiplied. I took the number of people and I multiplied by 2.5, and that gave me 250. Any questions on that? So the number of people, that's n. The 2.5, that's the average or mu. So here comes the big central limit theorem for sums. The sampling distribution for sums from samples of size n has mu sub. Have you seen this symbol before? You seen that in math? Okay, some of you have. Okay, that the way you read that is sum. It's actually a capital sigma. Okay, or the total of all is another good word. So mu sub sigma x, capital sigma x, or mu sub sum of x is equal to n times mu. And then sigma sub capital sigma of x is equal to sigma times the square root of n. To let you know why that's true, if you take sigma divided by the square root of n and multiply by n, you get sigma times root n. So algebra, you may not remember it, but that is algebra. Okay, it's simple algebra. Okay, and it turns out this is for quantitative stuff. You can't add no, you can't add yeses and nos. You can add only quantitative data. If the population's distribution is normal, or if the sample size is large, then the sampling, and large means over 30 in this case, so it's quantitative, then the sampling distribution for the sums is also normal. Okay, so basically it's the same as when we had averages. Okay, what I'm not doing in this class is proving anything, but you can believe me. Okay, you need to be a math major basically to prove this. Any questions Any questions on this? Okay, another way of writing it is capital sigma, which is your sum variable, is normally distributed with mean n mu and standard deviation sigma times root n. All right, so now comes the most important, at least that I've seen, examples where the sum is more important than the mean. And that is if you're looking, if you're in business, you have a company or you have a restaurant, you don't care about the average amount the customer spends. You care about the total amount of money that all the customers spend because that's your revenue. That's how much money's coming in, is the total amount. Does that make sense? So that would be an example where sigma is more important than mu. Okay. And here comes an example. This is really important. So suppose that the average customer at a restaurant spends $33.23. Okay. And the standard deviation is $9.22. If 65 customers eat at the restaurant today, okay, so that's what you expect. What is the probability that the total revenue for the restaurant will be less than $2,000? Okay, and then what is the first quartile for the total revenue for a day? Any questions on the question? And again, if you're the owner of a restaurant or the manager of a restaurant, that you care about how much money is coming in because then you know how many people you can hire and all, whether you can afford a remodel, all that kind of stuff, because it'll help you on your profit. And maybe less than 2,000 a day, you'll end up not having a profit. Okay, so that's why you would care about something like this if you happen to be owning a business. Okay. And what is the first quartile for revenue for a day? That would be 25% of the time. How much money are you going to make? How much money are you going to bring in? Okay. So that's at least 25% of the time, how much money are you going to bring in? So not exactly 25, but at least 25%. You're going to bring in less than this amount of money 25% of the time. All right, so here's what we do. Sigma, we use essential limit theorem, is normally distributed. Okay. How do we know it's normally distributed? What's the important thing here? What's the important number that's given? To know that we have a normal distribution. Don't see you jumping in. Right here, 65. And notice that the survey question is, hey, how much money? How much money did you spend? That's quantitative. It's quantitative, then we can say 65 is greater than 30. So we actually can use the normal distribution. So that's why sigma is normally distributed. The mean, again, is n times mu, the mean sum. So the mean of all possible sums is going to be 65, that's n, times $33.23, because that's mu, because that was the average customer at a restaurant. The standard deviation will be sigma, that is 9.22, so 9.22 times the square root of n, times the square root of 65. Any questions on this idea? Any questions? Okay, so 60 times 33.23, I popped in a calculator, I got 2,145 and when I did 9.22 times root 65, I got about 74.334. Okay, so we want to find out the probability of total revenue being less than 2000. So what do we have to do at this point? Hopefully it's obvious. What's the next step? Don't see you jumping in. We go to our calculator. I think the easiest, I'm going to hit refresh and that'll erase everything. Okay, we have a normal distribution, so it's a normal distribution calculator. The mean was 2,145. I'll copy and paste that in. The standard deviation was 74.334. Okay, we want the probability. Okay, we want the probability of being more than 2,000. So I'm going to go greater than, and then 2,000. And hit calculate. And there we go. Probability is about 0.97. Okay, and by the way, it does draw the normal distribution. You can kind of see what this is. Okay, so 0.97 is our probability. So we can say there's a probability of 0.97 that the total revenue will be less than 2,000. Did I write that down? More than, sorry. Should be 0.026 or so. Yeah, 0.026. Apologize for that. Had it backwards. Okay, or about 2.6% chance. Okay, so that's important for the restaurant manager, okay, or the owner to know. So that means it could happen, but it's not going to happen very often. Does that make sense? Okay, now we want the first quartile. All right, so if it's the first quartile, then what's the probability of being in the first quartile? That's easy. You don't need to do any calculation. You're supposed to just know it. What's the probability of being in the first quartile? Or less than the value of the first quartile? Yeah, close. 0.25. Not 25, but 0.25. Okay. So now 0.25. Want less than? And I hit calculate. And I get $2,094.86. Okay, I'll even put a dollar sign in that. Any questions on that? So 25% of the time, there's going to be less than $2,094.86. Okay. All right, so now between what two values will there be an 80% of the sample mean lying between? Sorry, not sample mean, of the sample total or sum lying between. How do we find that out? How do we answer that question? That one's got a little work to do. Any ideas? Okay, let's think about it. If 80% is in the middle, then 20% is outside. How much is on the left? If 20% is on the outside of the middle, how much is on the left? What percent? This should be easy. Don't see y'all jumping. If 20% is on the outside, then 10% is on the left. Half of that, because there's left and right for the outside. So 10% is on the right or left. And note 10% is on the right, right? Because this is a normal distribution, and normal distributions are symmetric, so left and right are equal. If they total to 20%, then they're both 10%. Okay, so then we just go and we say the probability of X being, we don't know, less than something is 0.1. And let's find out the value. And we get $2,049.74. So 204974. If I want the right, 10% on the right, then instead of being less than, I want 10% to be greater than some number. I'm going to erase that and hit calculate. And I get $2,240.26, 224026. And there is our 80% of the middle. So 80% of the sums will be between $2,049.74 and $2,240.26. Anyone lost on that? Anyone lost? Okay. Okay, I do want to remind you, use this calculator. Okay. If you start doing things by hand, you're going to have all kinds of round off errors and it's just not going to be right. And you're not going to have the right answer. You're going to lose points. Use this calculator. This does lots of decimals and it's perfect. And it's what I want you to use. Okay. All right. Not too bad. Here's the secret word. Okay. Technically, I guess it's not a secret word. It's a secret acronym or something. Secret initials. It's CLT. What does CLT stand for? Yeah, central limit theorem. I told you it's the most important theorem of all of statistics by far. It's not debatable. Everybody knows it. All statistician people know it. Central limit theorem is the biggie. Okay. And there's a guy named Gauss that kind of did this stuff, but I'm not going to get into it. But central limit theorem, CLT. Okay. Don't put whole words in, just CLT will be the secret word. Okay, so I want to give you big reminders, and that is you're all going to have this chapter due. There's no quiz this week. You're going to have discussion post assignment to do, but the big thing is the project. Okay, don't wait until the last minute to do the project. Okay, the hope is maybe tomorrow you'll send me a draft, and I'll give you feedback. Maybe even tomorrow. Might take a day, but I actually have a pretty light day tomorrow. I have a heavy day Wednesday, but a light day tomorrow. And I'll probably give you feedback tomorrow if you send it tomorrow morning, for example. If you send it tomorrow night, I'll be asleep, but it won't be for a while. But and then I'll give you feedback, and then you can make modifications. Okay, so that's a big deal. I also want to remember I only look at one draft that's emailed to me. Okay, so I give you feedback. and then you will do a final submission onto Canvas. But don't send me another email with another draft saying, "Can you look at my second draft?" Um, that I won't do. If you post a question about something in the project discussion forum, Project One discussion board, then I'll answer, I'll do my best to answer that question. Okay. And I'm online a lot. Yeah, actually yeah, if you send it by tomorrow, you'll definitely get feedback. It might take a couple days if you send it tomorrow night, for example, if a lot of people send it, because, there's only one of me. The latest possible time is 8 a.m. Thursday, but it could take a couple days for me to read it. And I do want to give you another heads up. Sunday, I'm actually I'm on the board of the Boys and Girls Club for our area, and we have our big fundraising event, and I'm going to be volunteering all day on Sunday. So I'm going to be pretty much offline Sunday for all day, helping. The good thing about this particular all Boys and Girls Clubs is no one's against it. Helping out children is not something people say, "How could you do that?" But I'm going to be doing that on Sunday, so if you ask me questions on Sunday, you may not get an answer until Monday, which is after it's due. So don't, your goal should be like have it completely submitted by Saturday even or Friday. Because if you can send me a draft, tonight or tomorrow, then you'll have time to do it. And then by Friday, you'll be able to get that draft in. Get the final one in. Okay. So I am going to stop the recording, but I'm always happy to answer questions if you have them.